So let's begin the class, that is acids and bases. So generally we come across many kinds of acids and basic materials in your daily life, like carbonic acid, some of the hydrate this carbonated water, or citric acid in some of the citrus fruit like orange or lemon, or acetic acid in the form of vinegar, or ascorbic acid as vitamin C, and some of the basic materials like toothpaste or uh, soap, etc. So generally we know that acid materials are sour in taste, and they turn blue litmus into red, or they react and corrode metals. Similarly, base are bitter in taste, they turn red litmus into blue, and they feel soapy or slippery. So generally, according to the syllabus, it gives some of the concepts of acids and bases like Arrhenius, Lowry-Bronsted, Lex Flood concept, solvent system concept, Lewis concept of acids and bases, and some of the relative strength of acids and bases, leveling effect, and Pearson hard soft acid base principle. So generally this acid base concept was introduced by the famous scientist Anthony Lavoisier. So the simplest scale is pH scale. So pH 7 is found to be neutral, less than pH 7 is found to be acidic, and more than pH 7 is found to be basic in nature. So as per the syllabus, the main topic is different concepts of explaining acids and bases like Arrhenius concept, Lowry-Bronsted concept, Lex Flood concept, solvent system concept, and the Lewis concept. The first one is the Arrhenius concept of distinguishing acids and bases. So according to this concept, a base releases H plus ions into water, and an acid releases H plus ions into water, and a base releases hydroxide ions into water. For example, if you take HCl in water, because HCl in water releases H plus ions into water, forming hydronium ion, that is H3O plus, and chloride ion. Or you can represent HCl in water, giving H plus into water and Cl minus. Since HCl liberates H plus ions into water, or it forms hydronium ion, HCl is termed to be an acid. Another example is acetic acid. If you treat acetic acid in water, again it forms hydronium ion, so we can say that this acetic acid is an acid according to Arrhenius concept. So you can take an base, for example sodium hydroxide. If you treat sodium hydroxide in water, because Arrhenius concept can be explained only in water, so if you treat sodium hydroxide in water, again you can see that it produces hydroxide ions. Since sodium hydroxide liberates hydroxide ions in water, it is an best example for base. Another example, you can take NH3 ammonia. When you treat ammonia in water, it forms ammonium ion as well as hydroxide ion. Since again it forms hydroxide ions, ammonia is a basic material. So next type of concept is Bronsted-Lowry concept of acid and bases. So according to this system, acid donate H plus ion and base accept H plus ion. So an acid is a proton donor and base is a proton acceptor. So you can have a this HA indicates the acid and B indicates the base, giving HB plus, that is its conjugate acid, and A minus as a conjugate base. So usually this Lowry-Bronsted concept always associated with conjugate acid base pair system. For example, if you take HCl and ammonia, HCl is acid, sulfuric hydrochloric acid is an acid, and ammonia is a base, so it reacts to form NH4 plus ammonium and chloride ion. So HCl and chlorides are the conjugate acid base pair. NH3 and NH4 plus are the conjugate base and acid pair. Similarly, if you take HCl and water, HCl is an acid. It releases H plus, so it's an acid, and this H2O is accept the H plus, so it becomes a base. Similarly, if you comes to the other side, on the other side of the arrow, again you can see a conjugate acid and base pair. So here this hydronium ion H3O plus is the conjugate acid, because it can release an H plus ion, and the Cl minus can easily accept the H plus ion, so that becomes a conjugate base. So always Lowry-Bronsted concept is associated with a pair of conjugate acid and base. So this is another example, like ammonia and water. Again you can see a conjugate acid base pair. So we can have some more examples like nitric acid and ammonia. Here I have given the three-dimensional structure of the molecules, as well as the chemical structure, the structural formula of the molecule, like nitric acid, how satisfying its valency and lone pair of electrons, ammonia, ammonium, and nitrate ion. So this is another example of Bronsted-Lowry acids and bases. Again you can see a pair of conjugate acid base. So another example, like nitric acid and water. Here nitric acid is an acid and water act as a base, and again you can see the conjugate acid base pair. So similarly you can take one more example. In the previous slide we have used HNO3 and water, where water was acting as a base, but when you treat with ammonia, water is acting as an acid here. Again you can see that ammonia, I have given the three-dimensional structure as well as the molecular chemical formula, structural formula. Here water is acting as a base. So water is having a peculiar property of acting as both acid and base, so it is called as amphoteric in nature. So water is a amphiprotic, or water is act as amphoteric in nature. So water can release H plus ion, and it can act as a acid, or it can accept H plus ion, and it can act as a base. Another kind of example for amphoteric substance is bicarbonate. Bicarbonate can release H plus to form carbonate, and it is a acid. It is acting like an acid. Similarly, it can accept a H plus ion to form carbonic acid, so it can act as a base. So you have water as well as bicarbonate as an example for amphoteric substances. So I told you always this Lowry-Bronsted concept is associated with a conjugate acid base pair. So generally stronger acid, the conjugate base will be weaker in nature. Similarly, if the base is weak, if we have a weak base, the conjugate acid will be strong enough. Okay, so here have another example is HCl and water. So the HCl is strong, and the conjugate base is weak. If conjugate acid is strong, the base will be weak in nature. So similarly, if you take this conjugate, this acid and this conjugate acid, if you compare HCl as well as hydronium ion, HCl is found to be more strong enough, so usually the equilibrium shifts towards right. For example, if you take acetic acid as well as hydronium ion, this hydronium ion is found to be more strong than the acetic acid, hence the equilibrium shifts to left. So after this Lowry-Bronsted concept, let us move on to the another concept, that is Lex flood concept. So this Lex flood concept is explained in terms of oxide ions. So acid is an oxide ion acceptor, while base is an oxide ion donor. If you take this silicon dioxide and calcium oxide, and it forms a calcium silicate, you can see that this oxide from the calcium goes to the SaO2. So this SaO2 is an oxide ion acceptor and it becomes an acid. Since calcium oxide releases or donates an oxide ion, this calcium oxide is a base. So you have another example like sulfur trioxide, SO3 and lead oxide to forming lead sulfate. So SO3 is accepting a oxide from the PbO, so SO3 becomes an acid and PbO becomes a base. Similarly, if we have one more example like carbon dioxide and magnesium oxide, here it forms a magnesium carbonate. So this carbon dioxide is accepting an oxide from the MgO, so this becomes a base. Since this Ca2 is accepting a oxide, it becomes an acid. And the next type of concept is solvent system. So before explaining this solvent system, you should know a solvent, how it is being ionized. So that is the auto ionization. For example, if you take water will be self ionized into hydronium ion as well as hydroxide ions. So according to this system, an acid is a substance which gives a cation characteristic of that solvent. So that means an acid gives a solvent cation and a base gives a solvent anion. For example, if any substance dissolved in water, if it is giving a solvent cation, that is hydronium ion, that is an acid, and if any substance dissolved in water and if it gives a solvent anion, that is hydroxide ion, that is a base. So here is example. If you treat HCl in water, it gives a hydronium ion, so this is the solvent cation, so HCl is a acid. Similarly, if you treat sodium hydroxide in water, it gives a solvent anion, that is OH minus ion, so NaOH is a base. So let us have another example. Another example is liquid ammonia. Liquid ammonia is will undergo ionization, self-auto ionization to form the cation, that is solvent cation is NH4 plus ammonium, and the solvent anion is the amide ion, NH2 minus. Suppose if you take NH4Cl, ammonium chloride, liquid ammonia, it forms a solvent cation, that is NH4 plus, hence NH4Cl is an acid. Similarly, if you take potassium amide in liquid ammonia, it releases amide, so there is a solvent anion, so potassium amide is a base. And finally, let us get to the next concept, that is Lewis concept. So generally we explained Arrhenius concept, that is based upon the in water as a solvent. Lowry-Bronsted based upon the donation of H plus or accept of H plus ion. Lexford again acceptance or donation of oxide ion. Solvent ion is based upon the solvent depending upon the solvent cation or release of solvent anion. But there are certain kinds of neutral molecules which found to be acid or base. So generally this Lewis concept is usually used in organic chemistry. So this scientist Lewis explained as an acid donates electron pairs and base accepts electron pairs. For example, if you take a BF3 and ammonia NH3, you can see that ammonia is having rich in electrons, so it can donate electrons to BF3. Since ammonia is donating electron, ammonia is a base, and BF3 is accepting the pair of electrons, it becomes an acid. So it can be denoted as BF3.NH3. Similarly, since ammonia is donating electrons to the electron deficient BF3, you can use a dative or coordination bond from ammonia towards BF3. So another example, you can take simple H plus and ammonia, and H plus is electron deficient, so it can accept the electron pair, so it becomes an acid, and NH3 is an electron pair donor, so ammonia is a base. So generally we can say that all cations are Lewis acid, because since they are electron deficient, they can accept electrons or they are electrophiles. All cations are termed to be Lewis acid. And one more point, like small cations like H plus and Ag plus are found to be strong acid than the larger cations like barium and calcium, which are found to be weak acids. So you can have, as I told, some of the neutral molecules which are found to be acid in nature. For example, BF3 and AlCl3, because in both BF3 and AlCl3 the central metal atom uh, is found to be or have a tendency to accept electrons pairs towards themselves to attain a octet configuration. BF3 boron is having electronic configuration 2s2 2p1. If at all it accepts 3 more electrons from fluorine, it can accept 2 more electrons, so it shows a tendency to accept electrons from the NH3, and NH3 is a base and BF3 becomes a acid. So another kind of examples for Lewis acid, that is an atom with vacant d orbital. The best example is silicon. If you take SiF4, you can take 2 more fluoride because they have a valence d orbital, because silicon is having atomic number 14. The outermost configuration will be 3s2 3p2. So it have a vacant d orbital, so it can take 2 more fluorides, so it becomes SiF62 minus. So SiF4 is a Lewis acid. So another type of Lewis acid are any central atom bonded to more electronegative atoms through multiple bonds are Lewis acid. For example, carbon dioxide, because carbon dioxide is a central metal is a carbon which bonded to 2 oxygen by a double bond. So this is a Lewis acid because it can accept electrons from the OH to form the corresponding analog. Similarly, sulfur dioxide is a central atom bonded to 2 electronegative oxygen through a double bond. So SO2 is another example of Lewis acid. So that is today's class, because we have explained what is Arrhenius concept, Lowry-Bronsted concept, and Lexford concept, and solvent system concept, and Lewis concept. For any queries and doubts, you can call me in this number, or you can mail to me at the following Gmail.